My name is Chiara. I'm working for European Bioplastics. You're looking at my first slides, and this is let's say, the final talk of the European Bioplastics series that we had in 2026. And we are talking about material solutions beyond packaging. So today we have two speakers with us, talking about medical devices and hygiene products. But before I get to the speakers, I would like just to walk you through a little bit of promotion for what we do and also some formats that are coming up if you would like to keep on belonging to this community. European Bioplastic is an association that is representing the interests of the bioplastic industry. We are a trade association along its entire value chain, mostly in Europe, but we also have some members outside Europe. We were born in 1993, so it's some time now. And today we collect around 75 members working in different roles. And we are actually striving for better legislation for the bioplastic sector. And this is why we bring different stakeholders and players in dialogue with each other, also through this kind of formats. Now it's time for your smartphones to come into the game, because I got two QR codes for you to scan. If you point at the first one, this is like a reminder to register for the annual conference that is taking place on the 1st and 2nd December 2026 in Berlin. And this is what my colleague Denise is organizing. And this is where you will find all the different information about our program. The second QR code is instead an invitation for you to send an abstract for this conference. This is where the abstract is open. Sorry, I'm seeing the screen of somebody here, not mine. I'll share again mine. So this is where you will see that there is a QR code for accessing the page where the different abstract submission is open until the 14th of July. So don't be shy, and we're looking for excellent speakers and contents, and we would like to hear your voice and know about your research and innovation. We also would like you to remind you that we have some innovation awards as well, where you can also send your own application. It's a very short application, but we're looking for outstanding concepts coming up from research institutions, but also companies that could fit into the boxes that we have, the categories that we have in place. And this is where you can also look at the conditions for this award. We have one award that is awarded each year at the conference. So if you would like to submit your application, this is also a very good time until the end of August. This format, just a disclaimer, this format is a format that is funded through several European funded projects. That's why the symbol of the flag of the European Union is there. The authors of the different talks, they are fully responsible for their talks and their content. So our European bioplastic point of view is not coming here into the game. And neither the European Union is responsible for the views and the contents that are shown by the authors in this case. Usual structure that we follow for these talks. So I'm buying some time for people to come in. So you're good in time. I buy another minute of your life. Will be the moderator also of the Q&A. We have today two experts with us that will give the presentations, and then we go into a joint Q&A with the two experts. And I just put some reminders here of new formats that we are proposing starting from September. We're going to a summer break now for the rest of July and August. But we resume the activities of these online talks. They're all for free on the 8th of September 2026, and we will be running the new series on the recycling of bioplastics with a talk about enzymatic recycling with colleagues from IMPLUS. And just for the housekeeping. So all your microphones are unmuted. This is on purpose. So this will be set like this for the entire format. You can use the chat to type any question you would like to address to both speakers or one of the speakers. This can be done anytime, and then we will go through the questions during the Q&A session. And you can also, if I know and you would like to speak up and you would like to ask one question and reopen your microphone, for instance, this is also possible. You need to raise your hand. So this is also what we will do during the Q&A. But the talks is something that we just, we let the speakers talk until the end, and then we gave a little bit more interaction into this format. Today, I'm very honored to have here Alberto Lopez-Gil. He's working for Selmat, and he will be talking about biofoams applications, mostly in the medical sector, but he's got also some, let's say, this kind of foams have been used also in other contexts. So this is something that we can also translate in other applications. And then we got Crystal Beckers from Total Energy Scorpion, and she will be talking about the applications of bioplastic into hygiene products. And she will give some examples about also some network and clustering activities that are emerging from the innovation that Total Energy Scorpion is doing. So I stop sharing here my presentation, and this is where I would like to give the floor to Alberto. Alberto, I'm putting you in the spotlight so that you can...
For the introduction, for the kind introduction. So I will start now with this presentation, with this talk, which is, as Chiara said, about the novel biofoam application in the medical sector. So, well, first, a brief introduction about our company, who we are. So we are a small company in Spain, in Valladolid, in this city, which is quite close to Madrid. We started as a spin-off company from the University of Valladolid, but then we have been growing during the last few years, and well, we have now 2 facilities. The last one is an industrial facility where we have not only specific characterization equipment, as you can see here, to understand foaming mechanisms in foam. This is a polymer with a good foamability. This is a polymer with a bad foamability, but also foaming pilot line. This is something we have been specializing during the last years in designing and building specific equipment to produce foams using any foaming technology in industry. And this is equipment quite versatile to accelerate foam development. This is an example, extrusion foaming. You will see later more example. And what we do is basically we support companies in this market, in the foam market, to develop more sustainable products and more advanced products. We help companies in the whole value chain, raw material suppliers, foam manufacturers, and end users of the foams. And well, why foams? On the one hand, because they are very interesting materials from a scientific perspective. As you can see here in this X-ray tomography reconstruction of the cellular structure. This is also an equipment we have to understand the cellular structure of foams. Foams are very complex materials. They are two-phase materials. There is a polymer, there is a gas, but the gas is low-density foams. Most of the foams in the market, more than 95% of the material, and the gas phase is arranged into a very complex cellular structure, which is not easy to analyze. We have tools to analyze this with accuracy, and this is important for the physical properties of the foams. On the other hand, because they are strategic materials in many sectors and applications, depending on the structure. If it is a closed cellular structure, we can use them in buildings for thermal insulation, for instance, in packaging, in food packaging, in sport products. For instance, the sole of running shoes are foams, as you can imagine. And then if the cellular structure is open, is interconnected, this is an example, they can be used as acoustic insulators, in comfort applications, generally matrices, and in car seats, but the range of application broaden when the cellular structure is open. In essence, 10% more than the foam market is huge. So this is a number, but more or less, it's a rough number, but more or less around 10% of the world plastic production is dedicated to the production of foams. If we consider the volume, the density of these products, this represents 50% of the whole plastic market in volume. However, these products, in many cases, are not circular, or they represent at least environmental challenges. Many of them are common to any plastic product. Most of the foams in the market are produced from fossil-based polymer, for instance, polystyrene foams, polyurethane foams. This is clear. Secondly, the recycling of these materials is not easy in many cases because of the high gas content. It's not easy to get rid of the gas for recycling. In addition, most foams are cross-linked. They need to be cross-linked to achieve low density. So they, in the end, they are thermosets, difficult to recycle. The volume is very high, as I said before. So they occupy large spaces in landfills when they are finally discarded. This is an example in what you can see in this picture. And concretely and associated to expanded polystyrene, for instance, they release lightweight microplastics that can be accidentally dispersed in the environment. And this is also a huge concern, specifically linked to foams. This is why we believe in CELMAT and in general terms that bioplastics are very promising circular solutions in the foam market. However, there are some drawbacks that are avoiding so far the penetration in the foam market of biopolymer and bio-based formulations. Here you can see some of them, moisture sensitive. They are moisture sensitive, and this is not possible in certain products. The thermal resistance is lower. The performance at the same foam density is usually lower with some biopolymers. And in general terms, they need modification to improve foamability. And this is because there are not yet many grades specifically developed for foaming. And foaming, a polymer for foaming needs to withstand very stringent requirements. But finally, and this is common to most applications of foams, the cost of the biopolymer is very high, and the foam market is dominated by commodity polymers, as I said before, by polystyrene, for instance. And this is so far the main market entry barrier in massive plastic use applications for foams. Here you can see how the foam market is divided by sectors. Most foams are used in the building sector, as I said before, for thermal insulation, acoustic insulation, automotive, expanded polypropylene, polyurethane foams, packaging, mainly dominated by polystyrene foams, but also furniture and bedding. But there are other applications for foams in which maybe the cost of the biopolymer is not such an important drawback. For instance, thermal insulation under very stringent conditions. And let me explain why. Here you see the main polymer foams that are used for thermal insulation under conventional conditions. When I say conventional conditions, I'm referring, for instance, to the temperature. These foams need to withstand in real application conditions. For instance, these conventional foams are good at providing good thermal insulation, very low lambda values within this range, at temperatures within -20 up to 45 degrees. We can say these foams are able to cover a good thermal insulation in many different regions of the world. And this is because these materials are designed with very low densities on purpose. As you can see here, this is a graph plotting the thermal conductivity of many materials used for thermal insulation, not only foams, versus density. And as you can see here, there is an optimum range of densities in between 30 and 55, 60 kilograms cubic meter, in which these foams for thermal insulation are designed. And this is because by reducing the density, we increase a lot the air content into the foam above 90, 70%. And by doing this, we suppress the contribution of the solid material to the thermal conductivity. This is the thermal conductivity of a material, which is composed by the thermal conductivity of the gas phase, the solid phase, radiation, and convection. So by increasing the air content, by reducing the density, within this range, we can suppress or reduce a lot the contribution of the solid polymer, polystyrene, polyurethane in this case. And moreover, these materials are designed to be closed cell and to have cell sizes within this range, 50, 500 microns. And by doing this, we can also suppress the radiation term and the convective term. So in the end, we have basically the thermal conductivity of the gas, which in this case is air. We have foams that are very good for thermal insulation under normal or conventional climate conditions, I would say. However, there are some applications for thermal insulation in which the conditions are more stringent, and this is the case of the refrigerated transport of vaccines. There are more things that need to be, more medical products that need to be transported under very low temperature, but this is probably the case that we have more we have closer in time because of the COVID pandemic. And we knew, we all know this, that these vaccines in many cases needed to be transported at a very low temperatures if they wanted to come to our health facility where we have finally the vaccines. We are talking about temperatures, as you can see here, very low. So these are very stringent conditions for the thermal insulation material. And moreover, the transportation time is very long. We need to keep the product at very low temperatures during the whole process of transportation until the health care facility. And finally, this is also important, the space for thermal insulation in these packages where the vaccines are packed, are stored during transportation is quite limited. We are talking about very low thicknesses to put our thermal insulation material inside. And this is not the case in other applications for thermal insulation where we can play with the thickness to increase the thermal resistance. So it's clear that in this application concretely and in general in the transportation of refrigerated products, generally vaccines, remedies, we need ultra-low thermal conductivity materials, allowing us to have lambdas below 10 megawatts, milliwatts meter Kelvin. So we believe this is in this case, the cost is not such a high requirement for the polymer use or for the foam. So maybe this is an opportunity for bio-based polymers. So what super insulating material can we use in this application? There are some possibilities in the state of the art. One of them is aerogels. We all know them. They are the lightest materials in the world and the materials with the lowest thermal conductivities, but they still face some issues. However, there is another material which is a vacuum insulation panel, which is already being used and it is already industrially produced for this application in which we need very low thermal conductivities. This is in essence a vacuum insulation panel. It's a sandwich material in which we have a core which and a layer, an aluminum layer on top. So in essence, we have a sandwich structure. And as a core of the vacuum insulation panel, we can have nanometric silica particles, which are compacted. This is a typical product in the core of the vacuum insulation panel, but we can also have a foam, which in this case is not a closed cell foam, as we said before, for conventional thermal insulation application. This is an open cell foam because we need to evacuate the air, the gas inside the foam using vacuum. When this foam is tightly sealed with the aluminum phase, then we get a super insulation materials because basically we have suppressed the thermal conductivity term associated to the gas phase. And we are basically having a thermal conductivity close to zero because we don't have air inside. This is the atmospheric pressure at which a conventional thermal insulation material is subjected. Normally, by using vacuum, we are getting rid of the gas inside the foam, so we are having a very low thermal conductivity within these ranges. And we do this by using very low insulation thicknesses between 6 and 25 millimeters. So this material is ideal for these applications, the refrigerated transportation of medical products such as vaccines, in which, as I said before, we have very low spaces. One issue of vacuum insulation panel is that maintaining vacuum for long times is not easy. It's because this aluminum layer in many cases is broken during the use of the product, and then we have air again inside the foam. So the lifespan of this product, as opposed to other thermal insulation materials, for instance, in the building sector, is shorter. So this is again a new opportunity for bio-based and compostable, and maybe in this case, compostable polymers. And another issue with vacuum insulation panels is that very high vacuum pressures are needed to remove the air inside, as you can see here. with conventional foams with these cell sizes. So the energy consumption in the production of the vacuum insulation panel is very high. So the final product cost is also very high. How can we reduce the vacuum needed to remove the air inside the foam? One, the best strategy is to reduce the cell size to the nanoscale. By doing this, as you can see here in this graph, where we see the gas thermal conductivity and the pressure, the vacuum pressure, by reducing the cell size from 100 microns to 50 nanometers, which is this line, we can reduce enormously the vacuum needed. So now the product is more, the energy required to produce the vacuum insulation panel is lower. And this is something we have already done. We have been able to produce nanocellular polymer foams that are very promising for this application. The cell size is below 200 nanometers. So what you see is like a solid panel. So you don't perceive this material as a foam. But if you look at the micrograph, at the microstructure inside, you see that this is a foam. This is a technology and cell technology that we have developed. The thing is that we need very specific technology. We need supercritical foaming using very high pressure, long foaming times, and polymers specifically developed to uptake large amounts of carbon dioxide, such as PMMA. So the question is this possible? Can we produce this foam, nanocellular foam, with open cellular structure by using low pressures and foaming times, not the pressure sometimes we need to produce this foam, sorry. Yes, this is possible by reducing the size of the initial polymer we want to foam. And this is possible by using the bit foaming technology. This is a technology in which, instead of foaming solid sheets, large in size, with a prismatic shape, for instance, we are foaming tiny micropellets. Micropellets lower than 1 millimeter in size. This is the initial polymer. This is the vessel, which in this case is an stirred vessel. So the micropellets are suspended into water, and then the blowing agent is injected, carbon dioxide, and the gas, in this case carbon dioxide, is saturating is diffusing to the micropellets. And when the micropellets are fully saturated with gas, then we open a valve, and the micropellet expands into expanded bits, as you can see here, also very small in size. And finally, we need a thermoforming process to obtain a prototype. This is a prototype, a very small prototype obtained in our facility. But this process is already used to produce real products, such as expanded polypropylenes, for instance, used in the helmet of bicycles or in many car parts, for instance, in the boot of the cars. And well, this is we have a wide range of autoclaves, of high pressure vessels, stirred vessels for the bit foaming technology in our facility, with very different volumes, from 0.3 up to 5 liters. The thing is, okay, we know now that we can reduce the time and we can reduce the pressure to produce a foam using very tiny micropellets. But is it possible to produce a foam with an open cellular structure and a nanocellular structure needed in an efficient vacuum insulation panel using the bit foaming technology and using a biopolymer, in this case a PLA grade not designed for foaming? If we are able to fulfill all these requirements, we would have a very promising material for the core of a vacuum insulation panel, and then a very promising material for the refrigerated transport of vaccines, for instance. So we needed to come up with several ideas or several approaches to use several approaches to do this. If we wanted to have an open cellular structure using a conventional PLA grade, we came up with the idea of using particles, bio-based particles, in this case micrometric particles, such as native starch. So this is our foam at high densities yet, and the particles, in this case, native starch granules embedded into the solid polymer. As you can see here, this is an SEM micrograph of the native starch. The size is very small. If we have these particles in the walls of the foam, when the foam reaches very high expansions, if they are properly placed, these particles in the walls, maybe at very high expansion, maybe we can promote the breaking of the walls. This is the idea. So we have particles that are small initially, so that we promote foam growing. So we don't promote the collapse of the foam. We allow the foam to grow without collapsing. But then at the end, when the expansion is very high, these particles are able to break the cell walls, which in a very low density foam, they are very thin. The cell walls in a foam are around 1-2 microns in thickness. And this is what we do. We produce several blends of PLA with several contents of native starch particles. As you can see here, these are the micro pellets before the foaming process. And then we also needed to have nanocells in our final foam. So the approach we use is to induce the formation of crystals during the foaming process so that we could increase the cell nucleation density in the process. And we did this by foaming at temperature below the melting temperature of the polymer. This is the DSC of the different materials, different PLA grades we use. And this is the foaming window we use. You already see that we could increase crystallinity by having a starch in the formulation. But what we observe when we foam the different formulation with 3 different temperatures within this range, below the melting temperature of PLA, is that we were increasing the crystallinity of the PLA. And this is occurring at the moment when we open the valve and the polymer expands. So when the polymer expands, there are a lot of crystals in the polymer, and these crystals are inducing the formation of many cells in the foam. And this increment in the cell nucleation allow us to reduce the cell size a lot. These are the cellular structure of the foams we produce at 100 degrees. And as you can see here at this magnification in the PLA foam without the starch, we barely see the cells in the microstructure because they are very small. We observe that as we increase the starch content, we have more bigger cells in the cellular structure. And this is because these big cells are formed around starch particles that are not completely embedded in the solid matrix. But we also observe in between the big cells that there are very tiny cells, which are submicron cells or even nanocells, which are still open. So we are fulfilling the 2 requirements we need in our foam to be used in a vacuum insulation panel. We have very small cells, submicron cells, and even nanometric cells, and they are open. So this is a very nice achievement, and we are proving that by using a conventional PLA grade, using several approaches, different approaches based on formulation and using the right technology to produce the foam, we can have a very promising material to be used in this application in a high added value application, in this case, the refrigerated transport of medical products. So, well, these are just to finalize the presentation. This is with this foaming pilot line, the bit foaming equipment we have has been upgraded in a previous European funded project by Nanopoulos. So this equipment is upgraded to work with several biopolymers and even nano-based composites. So this is what the target in this project, to work with bio-based nanocomposites. And well, we have been able to produce foams by bit foaming using different biopolymers and with different cellular structures and cell sizes. Here you see some example rigid PLA with closed cellular structure within this density range, and flexible foams with closed cellular structures within this density range. And well, we have more foaming pilot lines based on physical foaming, which are very promising for the development of bio-based foams, because we don't use chemical blowing agents. We just use a physical foaming agent, which is not present in the polymer after the foaming process. And all these physical foaming pilot lines have been upgraded to work with bio-based formulations and biopolymers, gas dissolution foaming, supercritical foaming, bit foaming, the one we have been talking about, extrusion foaming, as well. We have 2 lines now, and also foam injection molding. And we will be very happy to use these lines to develop, or I would say in general terms, to accelerate the deployment in the market of biopolymers in the foam market, which is our ambition. So we are working a lot to have more biopolymers, more biofoams in the market, because this is something we know it is being pursued by many end users of these products. So thank you very much for your attention.